KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Neet, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, okay, in this class we start with discussion about de Broglie wavelength, right? Okay, ma? Right. So in this chapter, dual nature of light. In this chapter, dual nature of light. From starting onwards, we focused on the things. Photoelectric effect. Afterwards, work function, and then threshold frequency. Next, threshold wavelength. After completion of that, Hedge observations. Next, Hallmarks and Leonard observations. Einstein's photoelectric equation. Studying of Einstein's photoelectric equation, that is what effect of intensity and frequency. Then we discussed important formula. Afterwards, particle nature of light and wave nature of light, right? So these are the things we completed till now. Okay, ma? Right. So when a metallic surface exposed to the electromagnetic radiation, that is light, which is invisible form of energy, the emission of electrons takes place. Emission of electrons takes place from that metallic surface, right? So this is what we are calling it as photoelectric effect, right? Here, the minimum energy of incident radiation required to eject the electrons from metallic surface is defined as work function of that surface, and the minimum frequency of incident radiation required to eject the electrons from metallic surface is defined as threshold frequency. Next, the maximum wavelength of incident radiations required to eject the electrons from a metallic surface is defined as threshold wavelength. Threshold wavelength, okay, right. So these three are the important definitions, as I told already. After that, Hedge observations and Hallmarks and Leonard observations, right. So while arising the idea of photoelectric effect, what happened, right? That's what we discussed in Hedge observations and then Hallmarks and Leonard observations, okay, right. Afterwards, the very important equation, that is what Einstein's photoelectric equation, E is equal to W naught plus K maximum, right. E is the energy of the incident radiation, W naught is the work function, and K maximum is the maximum kinetic energy of the emitted electrons, right, okay. Afterwards, we discussed the effect of intensity and frequency of light and photocurrent, right. Intensity is directly proportional to the number of incident photons, is directly proportional to the number of emitted photoelectrons per time, is directly proportional to the photocurrent, is directly proportional to the distance square. Next case, if the frequency of incident light increases, stopping potential increases, but there is no change in the photoelectric current, okay, right. Now, afterwards, regarding the particle nature of light, the energy of photon E is equal to h nu is equal to hc by lambda, And you know the mass of photon is equal to E by c square, that is equal to h nu by c square is equal to h by c lambda. And momentum of the photon p is equal to h nu by c, that is equal to h by lambda, right. Next, number of emitted photons n is equal to p by e, and intensity of light I is equal to p by a, that is equal to e by a into t, right. So and again, you know, number of photons falling per second n is equal to p by e. So p is the power of radiation and e is the energy, right. Afterwards we discussed wave nature of light, right. So now still this class also is continuation to the wave nature of light. So there itself we have to discuss the important quantity, you know, de Broglie wavelength, right. So this formula whatever we had here, that is lambda is equal to h by p and h by mv. So this formula is very important, right. Very important for Neet exam and mains exam also, right. If you want, you go through the previous papers, you can check it how many times this formula is repeated, okay, right. So now we start with the discussion of de Broglie wavelength, right. So de Broglie is the name of the scientist, you know. According to de Broglie theory, the wavelength of de Broglie wave is given by, the wavelength of de Broglie wave is given by lambda is equal to h by p. You know, it is p is the momentum, that is the mass into speed or velocity, h by mv, that is equal to h by, you know, which is, you know, one formula, that is ke is equal to p square by 2m. But here he is using symbol E to represent kinetic energy of the particle, so that E is equal to p square by 2m, right. Then p is equal to square root of 2me, that only he is writing here, p is equal to square root of 2me. And from these three you can write lambda is directly proportional to 1 by p, because h is constant, which is not going to change anywhere, right. It is a Planck's constant. Then, you know, is directly proportional to 1 by v. This is what the mass, right. So for one particular situation, right, unless you are not changing the particle, so this mass is also constant, right. Then, you know, when mass is constant, 2 is constant, according to this you can write lambda is directly proportional to 1 by square root of kinetic energy of the particle, right. Here as I told you already, here itself, now itself, h is the Planck's constant, m is the mass of the particle, and v is the speed of the particle, right. h is the Planck's constant, m is the mass of the particle, and v is the speed of the particle, and e is the kinetic energy of the particle, okay, right. See this next, the smallest wavelength whose measurement is possible, the smallest wavelength whose measurement is possible is that of gamma rays, right. So for example, you know, you take whatever you want, you can take, that is what, like electron, proton, neutron and alpha particle, but generally the smallest wavelength whose measurement is possible is that of gamma rays. Next, the wavelength of matter waves associated with the microscopic particles, the wavelength of matter waves associated with the microscopic particles like electron, proton, neutron and alpha particle, etc., is of the order of 10 to the power of minus 10 meters, 10 to the power of minus 10 meters, okay, right. And next, so this is about de Broglie wavelength, right. So we had a formula for de Broglie wavelength to calculate in terms of mass and velocity, and in terms of mass and kinetic energy, okay, right. And after that, right, so the wavelength of matter waves associated with the microscopic particles, he has given the order, that is what, the order of minus 10 to the power of order of 10 to the power of minus 10 meters for electron, proton, neutron and then alpha particle, okay, right. Next, de Broglie wavelength associated with the charged particles, and after this we will discuss de Broglie wavelength associated with uncharged particles, okay, right. First we will discuss about de Broglie wavelength associated with the charged particle, okay, right. See here, the energy of a charged particle of a charged particle accelerated through potential difference V. The energy of a charged particle accelerated through potential difference V. That is E is equal to, here E means kinetic energy, E is equal to half mv square, that is equal to Vq or Qv, right? So this is we got it from the chapter of electrostatic also, right? From the definition of potential difference, right? You can write it as U is equal to Q into V, is the product of charge and is the potential difference, right? Hence de Broglie wavelength, the formula is same what we discussed here, that is what H by P, H by square root of 2me, and in place of E, because of this charged particle, right, it has a charge, and the potential difference through which a particle is going to accelerate, right? So in terms of charge and potential difference through which a particle is going to accelerate, you can write the formula for de Broglie wavelength like lambda is equal to H by square root of 2mqv, square root of 2mqv, right? And we have different charged particles, that is like those are like electron, proton, deuteron and alpha particle, right? So values are same. First the thing is Planck's constant is same, right, and mass will be different, and this is the charge, okay? So even though you are going to accelerate same potential, even though you are going to accelerate all of these, that is what electron, proton and deuteron and alpha particle, through the same potential difference, because of the difference in mass and because of the difference in charge, right? So the value of de Broglie wavelength is different. So that, right, approximately, you can write it as the same formula, you can write it as like this, that is what lambda electron is like 12.27 divided by square root of V angstrom unit, and then lambda proton is equal to 0.286 by square root of V angstrom unit, comma lambda deuteron is equal to 0.202 square root of V, 0.202 divided by square root of V angstrom unit, comma lambda alpha particle is equal to 0.101 divided by square root of V angstrom unit, okay? So these are the values of de Broglie wavelength for the particles like electron, proton, deuteron and alpha particle, okay, right? The same thing, same formula, but because of having different charge and different mass, just to, if you substitute, for example, if you want to find the de Broglie wavelength of electron, what is the mass of the electron and what is the charge of the electron, those two values you have to write here. V is same for all the particles. V may be different, but according to our discussion, V is same and H is constant. Then if you write the charge of electron and mass of electron here, you will get this value. Similarly, if you write mass of the proton and charge of proton here, you will get this value, right? And if you write the mass of deuteron and charge of deuteron here, you will get this value. Similarly, at last, if you write the mass of alpha particle and charge of alpha particle here, you will get this value, that is 0.101 by square root of V angstrom unit, okay? That is, right? So like this we are getting de Broglie wavelength associated with charged particles, like here electron, proton, deuteron and alpha particle, okay, right? Next, de Broglie wavelength associated with uncharged particles, right? So that is what neutron. See here, for neutron de Broglie wavelength is given by, for neutron de Broglie wavelength is given as lambda neutron is equal to, right? The formula is same. So whatever the formula we had here, that is same, but here formula we are going to modify according to the neutron. Then you can write it as lambda neutron is equal to wavelength of neutron, de Broglie wavelength for neutron is equal to 0.286 into 10 to the power of minus 10 divided by square root of E. Here this E we are taking in electron volt, this E value, energy value we are taking in electron volt. So finally unit of wavelength is meters only, that is what meters, okay, right? Suppose if the same thing you want to express in angstrom unit, we have to write like this, because 1 angstrom unit is equal 10 to the power of minus 10 meters, no? That's why here is equal to 0.286 divided by square root of E electron volt, right? Electron volt, and that is what angstrom unit, okay? 0.286 divided by square root of E, and E value we are taking in electron volt, and there itself it is angstrom unit, okay, right? And next, if you see this here, so these are the de Broglie wavelength values for neutron in terms of meters and in terms of angstrom units, okay, that is. See here. Next, you know what is the energy of thermal neutrons at ordinary temperatures, right? Energy of thermal neutrons at ordinary temperature, E is equal to K into T, right? Here K is the Boltzmann constant, T is the temperature, right? When E is equal to K into T, you know, if you substitute this value in the previous formula just now we discussed, right? And there you will get it as like this, that is what H by lambda is equal to H by square root of 3mkt, right? So lambda for thermal neutron is equal to, write down these values, this is what 6.62 into 10 to the power of minus 34 divided by square root of 3 into 1.67 into 10 to the power of minus 27 into 1.38 into 10 to the power of minus 23 T. So it will become like this, 25.17 divided by square root of T angstrom unit, okay? That is what we can say in terms of angstrom unit. The value of wavelength for thermal neutron is 25.17 divided by square root of T angstrom unit, okay, right? Next, here what is K? I already told you, that is what Boltzmann constant, okay? And you know what is T? Temperature, right? Absolute temperature. T is the absolute temperature, and the value of Boltzmann, you know, that is what 1.38 into 10 to the power of minus 23, right? So the units are like joule per Kelvin, okay, right? Next thing is, that is characteristics of matter waves, right? Characteristics of matter waves. So what are the characteristics of matter waves? That we will discuss now point by point, okay? See here, you know, the first point is, see here, matter waves represents the probability of finding a particle in space. Matter waves represents the probability of finding a particle in space, right? So in our surrounding space where the particle is present, so the probability of finding a particle in space is possible by using matter waves, okay? Next, second one, you know, matter waves are not electromagnetic in nature. Matter waves are not electromagnetic in nature, okay, right? You know, third point is de Broglie or matter wave. De Broglie or matter wave is independent of the charge, on the material particle, right? Okay, see here, de Broglie or matter wave is independent of the charge on the material particle, independent of the charge on the material particle. So what does it mean? It means matter wave or de Broglie wave, it means matter wave or de Broglie wave is associated with every moving particle, right? So the meaning of this information, that is what de Broglie or matter wave is independent of the charge on the material particle, means matter wave or de Broglie wave is associated with every moving particle, whether it is charged or not, right? de Broglie wave or matter wave is associated with every moving particle, whether it is a charge or uncharged. Just now in the same class, just before this starting of characteristics of matter waves, I explained you and we calculated, and I have given the formulas to calculate de Broglie wavelength associated with the charged particles and associated with the uncharged particle, right? That only he is saying here. Next, fourth one, practical observation of matter waves. Practical observation of matter waves is possible only. Practical observation of matter waves is possible only when the de Broglie wavelength is of the order of the size of the particles, right? Practical observation of matter waves is possible only when the de Broglie wavelength is of the order of the size of the particles, right? I will repeat once again. He is talking about the possibility. So the practical observing of matter waves is possible when the de Broglie wavelength is of the order of the size of the particles. He is comparing the wavelength of the de Broglie wave, de Broglie wavelength, the wavelength of the wave, and then that is with the size of the particle, right? So when it is that is comparable, then you can observe matter waves, okay, right? Next, fifth one, electron microscope works on the phenomena of de Broglie waves, which is very important. That's why I underline. Electron microscope is one of the advanced microscopes what we have nowadays, right? So the electron microscope works on the phenomena of de Broglie waves, right? Okay. What is microscope? What is the purpose of microscope? From our biology subject you came to know, right? In biology subject you came to know what is the use of microscope generally, right? And okay, so that's why here microscope means actually it is 10 to the power of minus 6. The order of the size of the things up to 10 to the power of minus 6 you can see with the help of microscope, but electron microscope is not like that. It is almost that is up to 10 to the power of minus 24. 10 to the power of minus 24, that is work by using the phenomena of de Broglie waves, right? Next, sixth one, the phase velocity of matter waves. The phase velocity of matter waves can be greater than the speed of light. The phase velocity of matter waves can be greater than the speed of light. Next point, matter waves can propagate in vacuum, hence they are of mechanical waves. Matter waves can propagate in vacuum, hence they are of mechanical waves, okay, right? Next, next point, the number of de Broglie waves associated with nth orbital electron is n. The number of de Broglie waves associated with nth orbital electron is n. That is what small n, okay, right? Next, see here, that is what last point from the characteristics of matter waves. See here, according to de Broglie's concept of matter wave, if we assume a wave behavior with electron, according to de Broglie's concept of matter wave, if we assume a wave behavior with electron, the circumference of the stationary orbit, the circumference of the stationary orbit must be equal to the integral multiple of wavelength of the wave associated with the electron. Okay, I'll repeat once again. According to de Broglie's concept of matter wave, if we assume a wave behavior with electron, suppose the electron is going like this, right? If we assume a wave behavior with electron, the circumference of the stationary orbit, right? It is what circumference, right? The circumference of the stationary orbit must be equal to the integral multiple of the wavelength of the wave associated with the electron. Okay, so when this theory is correct, you can write mathematically, 2 pi r is equal to n lambda. 2 pi r is equal to n lambda. Okay, and here itself, from this starting of this class, that is what de Broglie wavelength lambda is equal to h by mv, right? So when you write lambda is equal to h by mv, and mathematically you substitute here, that is what 2 pi r is equal to n into h by mv. n into h by mv, or the same thing you can write mvr is equal to n into h by 2 pi, right? So, from Bohr's theory, there are 3 postulates, right? So, this is one of the important postulate which is talking about the angular momentum, right? So, there we got it, mvr is equal to n into h by 2 pi or n into h cut, okay? mvr is equal to n into h by 2 pi or n into h cut, okay, right? So, this is what thus the de Broglie's matter wave, thus the de Broglie's matter wave concept is analogous to the Bohr's hypothesis, Bohr's hypothesis, okay, right? So, in this class we focused, is a very important class for even that is what, especially because it is Neet class, right? And in every class you have to concentrate on the formulas and any chance for arising conceptual bits, okay? So, here there is a chance for conceptual bit, that is what because we have important points, 9 points are here. Out of these 9 points there may be a chance to get any one that is what theoretical bit or conceptual bit, right? But at the same time we have some formulas, right? So, that is what de Broglie wavelength formula, and that is okay, I already told you lambda is equal to h by p. After that we got some other formulas. Those are formulas to calculate de Broglie wavelength for electron, right? And proton, deuteron, right? Afterwards alpha particle also, okay? So, like that we concentrated to discuss the de Broglie wavelength, right? So, here this is what electron, proton, deuteron and alpha particle. So, actually these are the charged particles. Here we calculated de Broglie wavelength associated with the charged particles, right? V is the potential difference through which a particle is going to accelerate, and as usually here h is the Planck's constant, right? M is the mass of the charged particle, and q is the charge, and v is the potential difference through which particle is going to accelerate, right? This formula also no need. If you want to calculate de Broglie wavelength for any of these 4, you can use these formulas directly. So, from this only we are getting all these things, okay, right? Similarly, next we went to calculate, that is what de Broglie wavelength associated with uncharged particle, right? That is what lambda of uncharged particle, for example neutron is equal to 0.286 divided by square root of e. Square root of e, e is we have to take in, that is what electron volt we have to take, and finally this will be available in angstrom unit, right? You can convert, it is not a problem. Conversions is not the matter. That is what we learned from units and measurement chapter, right? First year syllabus. So, conversions we should not keep in mind. The main thing is actually what is the formula, that is important, okay, right? So, after completion of this we came here to discuss energy of thermal neutron, energy of thermal neutron at ordinary temperature, okay, right? So, that is what lambda is equal to h by square root of 3m kT. Lambda is equal to h by square root of 3m kT, okay? And then this is the formula you can use directly. So, the temperature you can measure here, and you can calculate wavelength of thermal neutron, okay? Next here we discussed characteristics of matter waves, okay? So, here we had 9 important points, right? So, these 9 points talking about characteristics of matter waves, right? So, here itself you keep in mind. So, every point is important here, every point is important, along with the last point, that is very important. MVR is equal to n into h by 2 pi. Here he is comparing that matter waves, that is what de Broglie's information given for matter waves to the Bohr's hypothesis, okay, right? Thank you. We will continue in the next class.